First up on our journey is watching these skilled artisans build a giant bandsaw using techniques that have stood the test of time. Everything starts with creating incredibly detailed patterns, which work as the master templates for every single cast component. The magic happens during forging, that intense process where scorching hot metal gets shaped under tremendous pressure. Once that's done, the precision work begins with careful machining that cuts and shapes everything to exact measurements. It's amazing to see these craftspeople work with such confidence, their hands guided by generations of collective knowledge rather than computer simulations. Sandcasting might sound simple, but it's actually one of humanity's oldest metalworking methods, going back several thousand years. What's truly remarkable is that despite its ancient roots, it remains the dominant casting technique worldwide. The concept couldn't be more straightforward. Form a mold using sand, pour molten metal into it, and you've got yourself a shaped component. This approach is particularly vital when creating those enormous industrial pieces like massive engine blocks, intricate pump housings, and those colossal ship propellers you've probably seen in documentaries. These bulky components would be practically impossible to produce efficiently through regular machining or pressure die casting methods. That's exactly why sandcasting continues to reign supreme when manufacturing oversized complex parts at reasonable costs. The beauty of this method lies in its brilliant simplicity, using readily available materials to create virtually any metal shape imaginable with minimal specialized equipment. Crafting precise patterns and flawless sand molds by hand isn't just technical work, it's a genuine art form requiring years of practice and deep understanding. The real expertise lies in accurately predicting the behavior of both sand and molten metal throughout the entire process. Everything hinges on the initial pattern, whose quality determines the success of the whole operation. These master craftspeople understand a fascinating physical property: metal contracts as it cools down from its molten state. To compensate for this natural shrinkage, they deliberately make patterns slightly larger than the desired final product. This strategic oversizing, called contraction allowance, varies depending on the specific metal they're working with. This thoughtful adjustment ensures the finished piece matches exact dimensions once it's completely cooled and solidified. You can see the accumulated wisdom in their confident movements, each adjustment and measurement reflecting calculations they've internalized through years of practical experience rather than formulas from textbooks. The choreography of moving molten metal from furnace to mold is something to behold. Workers maintain precise temperature control as they transfer the glowing liquid to a pouring ladle. Too hot or too cold spells disaster. You can see the team working in perfect harmony as they carefully tilt the ladle, directing the flowing metal through the mold's channel system. After the metal solidifies completely, they begin the labor-intensive job of freeing the new casting from its sandy prison. In these traditional workshops, you'll often see the sand mold broken apart primarily by hand, occasionally aided by simple tools to lift away the top sections. The coordination between workers during this dangerous process is remarkable. They communicate with subtle gestures and knowing glances, their movements synchronized through countless repetitions of this delicate dance with molten metal that could cause serious injury with even a minor mistake. When first revealed, the raw casting is far from finished. It's covered with extra bits and pieces from the casting process. Now comes the crucial refinement phase, where all unnecessary material gets stripped away to meet exact design specifications. All those little channels and risers that were absolutely essential for guiding the molten metal are now just in the way. They'd interfere with the component's performance and need to be removed. Throughout this transformation, skilled workers gradually shape the casting to perfectly match detailed engineering blueprints. The whole operation requires not just technical expertise, but constant awareness of safety protocols. What's particularly impressive is watching how they improvise solutions to unique challenges that arise with each casting. No two pieces are ever identical, requiring creative problem solving that automated systems simply couldn't handle with the same flexibility and intuition. Cleaning is just as important as shaping when it comes to these castings. Beyond trimming away excess material, each piece needs thorough cleaning to remove any lingering sand, scale, or oxide layers that could weaken the metal or interfere with subsequent processes. This cleanup often involves smoothing out any rough edges or uneven surfaces left from the pouring process. This is where handheld tools really shine. Chisels, hammers, and compact grinders become essential, particularly when working with intricate designs or tight corners. where larger machinery simply can't reach. You can almost feel the transformation happening as workers methodically remove imperfections, their trained eyes spotting subtle flaws that most of us would completely miss. The rhythmic sounds of metal on metal create an industrial symphony that has remained largely unchanged for centuries, connecting these modern craftspeople to countless generations who came before them. Now we're watching the newly cast component get fitted with a threaded rod and hardware that makes it functional. The team starts by ensuring perfect alignment before carefully marking drill locations with remarkable precision. Using handheld power tools, they create openings that will accommodate the threading mechanism. After sliding in the threaded rod, they secure it properly with additional fasteners based on specific design requirements. Usually, they'll attach a hand wheel to one end, allowing operators to rotate it and move connected parts along the rod with smooth precision. Before final assembly, each bearing gets thoroughly inspected and lightly oiled for smooth operation, while the housing gets prepared so everything maintains perfect alignment during use. The focus in their expressions reveals how critical this assembly stage is. Even minor misalignments here would multiply into major operational problems later, so they check and double-check their work with patient thoroughness that modern production schedules rarely permit. Creating a flat surface on a massive cast plate poses unique challenges. This surface will serve as the foundation for the entire machine's operation and must be perfectly level. Typically, they'll secure the plate onto a specialized planing or milling machine with heavy-duty clamps. The cutting tool then moves systematically across the plate's surface, removing thin metal layers that curl away as shimmering ribbons of swarf. Once they achieve that flawless finish, the plate gets incorporated into the main framework. This marriage of perfectly machined surfaces with robust structural supports creates both stability and precise alignment, ensuring all moving components, whether they're sliding arms or spinning shafts, interact exactly as designed without unnecessary friction or wear. What's particularly fascinating is watching how the machinists constantly check their progress using simple but effective measuring tools, their experienced hands detecting minute variations that would be invisible to the untrained eye. These seemingly small imperfections, if left uncorrected, would accumulate into major operational problems down the line. After all the casting, machining, and assembly work is complete and everything aligns just right, the freshly constructed machine receives a protective coat of paint. This isn't merely cosmetic, it provides essential protection against rust and environmental damage, while giving the finished machine that professional, polished appearance we associate with quality equipment. What's truly fascinating is how these traditional methods, even without fancy computer-controlled systems, consistently produce machines with outstanding longevity and performance that many modern factories would envy. There's something profoundly impressive about watching equipment built largely by hand operate flawlessly for decades. For their second showcase project, we watched the team tackle a compressor crankshaft. It's remarkable that in our digital age of robotics and computer-controlled everything, these hands-on manufacturing techniques remain not just relevant, but essential. In certain industrial communities, skills like hand forging and manual machining aren't just jobs, they're cultural treasures passed through generations like family heirlooms. These artisans continue to forge and machine crankshafts entirely by hand, often using techniques and equipment dating back 3/4 of a century. This isn't stubbornness or resistance to progress, it fills real economic and practical needs. Local businesses thrive thanks to these skilled workers who can produce or repair heavy-duty compressor crankshafts without requiring expensive imported machinery. This approach supports regional industrial development by providing reliable, affordable components exactly when and where they're needed most. The resilience of these communities often stems from this very self-sufficiency. Their ability to create and maintain complex machinery without dependence on global supply chains or imported expertise gives them remarkable economic stability even during disruptions that might cripple more advanced production systems. The steel transformation begins with heating in furnaces reaching blistering temperatures. We're talking well over 1000 degrees Celsius, 1832 degree Fahrenheit for most medium carbon and alloy steels used in these applications. When the forging work completes, they transfer the roughly shaped steel to a lathe where excess material gets carefully removed and critical features like bearing journals and precise shaft diameters are cut to exact specifications. The intense heat of the forging process creates a distinctive glow that bathes the workshop in orange light, highlighting the focused expressions of workers who must maintain perfect timing and coordination. One misstep with metal at these temperatures could result in serious injury, yet they move with confident precision born from countless repetitions of these dangerous tasks. What sets these machinists apart is their reliance on highly developed sensory skills and decades of experience. They use specialized measuring tools like dial indicators, micrometers, calipers, and surface gauges to verify that each cut falls within incredibly tight tolerances. While working a crankshaft, they frequently stop the machine to take measurements, checking diameter, roundness, and alignment with meticulous care. Even microscopic deviations, literally measured in thousandths of a millimeter, could cause catastrophic balance issues or premature failure once the component enters service. This iterative process ensures each surface finishes smooth and flawless, free from tool marks or imperfections that could compromise performance. These master craftspeople have developed almost supernatural sensitivity to their materials and tools over years of practice. They can instantly interpret the sounds and vibrations during cutting, like a doctor with a stethoscope. These sensory inputs tell them immediately if there's an issue like chatter, tool wear, or material inconsistency. Their experience allows them to anticipate and correct potential problems before they affect the finished part, a level of intuitive understanding no computer program can replicate. Just when you think you've seen it all, these versatile artisans switch gears completely from industrial components to crafting a flawless automotive hood. The process begins by selecting premium sheet metal, typically high-grade mild steel or aluminum, chosen specifically for its ideal balance of strength, durability, and lightweight properties. Each metal sheet undergoes careful inspection before being precisely measured and cut, ensuring just enough material for forming while minimizing costly waste. Now comes the fascinating transformation through stamping and forming processes. A massive manually operated press converts flat metal sheets into beautifully curved, aerodynamic hood shapes. The team employs custom-designed dies and punches, often handcrafted using techniques preserved through generations. You can see the concentration on operators' faces as they carefully position each metal sheet in the press, where tremendous force gradually shapes the material to match the die's complex contours. Throughout this critical phase, workers constantly monitor how the metal flows into position, watching for any irregularities and making split-second adjustments to press alignment or pressure when needed, showcasing a level of hands-on control that fully automated systems simply cannot achieve. With the basic form completed, the hood moves to a critical refinement stage where excess material gets trimmed away and structural seams are perfected for both function and visual appeal. Here's where those stamping artifacts, those little ridges, flashes, and extra bits of metal extending beyond the desired profile, get precisely removed using specialized handheld cutting tools. The operators, drawing on collective decades of experience, guide these tools along the hood's contours with remarkable precision and control, eliminating only unwanted material while maintaining the stamped shape's integrity. Their goal, creating a clean, flawless outline that serves as the foundation for subsequent assembly steps, the difference between amateur and professional results. What's particularly impressive is the economy of their movements. No wasted motion or unnecessary cuts, just confident, deliberate actions that reveal the thousands of hours invested in mastering these specific skills. Even their body positioning shows deep ergonomic knowledge developed through experience, minimizing strain while maximizing control during these precise cutting operations. Once excess material disappears, focus shifts to preparing all edges and seams for welding. These critical junction points where separate metal panels meet require perfect alignment. The welding process demands extraordinary manual control to create consistent, strong connections throughout. These smooth, even welds contribute not just to structural integrity, but also to the hood's aesthetic quality, a hallmark of quality craftsmanship. After passing rigorous inspection, the completed hood undergoes thorough cleaning to remove any manufacturing residue before receiving protective treatments like corrosion inhibitors or clear sealants to ensure longevity. The welder's expertise is particularly evident in how they maintain uniform heat input throughout each weld. Too much heat would warp the thin sheet metal, while insufficient heat would create weak spots prone to failure. Their welding technique represents years of practice, with torch angles and movement speeds adjusted instinctively based on metal thickness, joint configuration, and even the ambient temperature and humidity of the workshop that day. Throughout our exploration, we've seen how Pakistan's incredible craftspeople consistently achieve world-class results despite limited access to cutting-edge technology. Their intimate understanding of metallurgy and material science enables them to fabricate enormous industrial components with astonishing precision. The process typically begins with substantial blocks of steel or iron, often locally sourced or cleverly recycled, each carefully evaluated for quality and consistency. Using traditional cutting methods like oxy-fuel torches or manual shears, they transform these massive metal blocks into manageable pieces suited to their forging equipment. These sections then enter decades-old furnaces fueled by coal or oil, reaching the extreme temperatures necessary to make even the toughest metals pliable enough for shaping. What's remarkable is how they've adapted their processes to work within local constraints, developing specialized techniques that maximize efficiency with the tools available, rather than viewing limited technology access as an insurmountable obstacle to quality production. Their mold-making technique starts with arranging standard bricks to establish the outer boundary. Then begins the meticulous work of compacting and shaping sand within this framework to create the precise negative form required. Each section of sand gets carefully contoured to ensure perfect dimensions throughout. They typically incorporate small vents or channels to release trapped gases during the metal pouring process, seemingly minor details that dramatically impact casting quality. The integrity of this sand mold directly determines the final casting success, as a properly compacted, accurately shaped mold prevents common defects, ensures even metal flow, and maintains correct component geometry, truly the foundation of the entire process. The mold makers constantly test sand consistency between their fingers, adding water or clay binders as needed to achieve that perfect balance between firmness for structural integrity and permeability for gas escape, a sensory assessment that takes years to develop fully and can't be replicated by moisture meters or other automated testing equipment. In today's mass production landscape, this traditional approach remains irreplaceable for certain applications. It offers unmatched flexibility and cost-effectiveness for creating massive, uniquely shaped industrial components that would be prohibitively expensive or technically impossible with modern automated equipment. By cleverly utilizing locally available materials like sand and ordinary bricks, these foundries can construct molds of virtually any scale or complexity. Human expertise remains the critical factor. Craftspeople who've dedicated decades to mastering sand casting can modify mold designs instantly during production, their specialized knowledge preventing common casting problems like gas porosity or incomplete fills that would compromise the finished component's structural integrity. The adaptability of these skilled workers becomes particularly evident when unexpected challenges arise. They can assess problems and implement solutions in real time, drawing from a vast mental library of similar situations they've encountered throughout their careers. This problem-solving flexibility represents a significant advantage over rigid, automated systems that can only follow pre-programmed responses to anticipated issues. While computerized production systems excel at repetitive, high-volume manufacturing, these time-tested methods provide extraordinary adaptability and problem-solving capabilities. This allows foundries to produce complex, one-off components with minimal upfront tooling investment. Traditional sand casting effectively bridges technological gaps by leveraging readily available local resources, establishing a sustainable, self-sufficient industrial production model. The skilled workforce adapts rapidly to changing specifications while ensuring consistent supply of critical machinery components that keep local industries running smoothly. These traditional methods also excel at accommodating mid-production design changes. If an engineer requests modifications after seeing the initial casting, workers can quickly adjust the mold for subsequent pours without the extensive reprogramming and retooling that would be required in highly automated systems. This flexibility proves particularly valuable in developing industrial settings where specifications might evolve as projects progress and where the ability to iterate quickly outweighs the benefits of high-volume standardization. This approach to self-reliance generates remarkable economic advantages for communities. By maintaining manufacturing capabilities locally, regions retain financial resources and create sustainable employment for a diverse workforce, from mold makers and forgers to machinists and quality control specialists. Beyond pure economics, this methodology preserves irreplaceable cultural and technical knowledge, the intuitive understanding of material properties, mold design principles, and specialized metalworking techniques developed over generations. In our era of increasing automation where human involvement often diminishes, these specialized skills remain invaluable for addressing unique manufacturing challenges that automated systems simply cannot handle effectively. There's also a profound social dimension to this knowledge preservation. These workshops often function as informal vocational schools where younger workers learn directly from masters through years of apprenticeship, creating not just technical skill transfer, but also community cohesion and cultural continuity that extends far beyond the workshop walls into family and neighborhood relationship. That's why, despite our incredible advances in manufacturing technology, traditional sandcasting continues as a cornerstone of industrial production worldwide. It provides a reliable, economical, and infinitely adaptable solution for creating the massive, complex components that form the backbone of heavy industry. Parts that would otherwise be impossible or financially unfeasible to produce through other means. The resilience of these traditional methods becomes particularly apparent during supply chain disruptions, when communities with preserved manufacturing capabilities can continue producing essential components, while regions entirely dependent on global technological networks may face prolonged manufacturing shutdown. After completing the casting process, finishing work on these gigantic industrial components becomes absolutely critical to their performance. As we observed earlier, excess metal gets carefully trimmed away with extraordinary precision. Even minor mistakes during this phase could introduce dimensional inaccuracies requiring expensive corrective machining later. Through meticulous removal of all extraneous material, they gradually refine each component's profile to perfectly match design specifications, establishing a clean, uniform foundation for subsequent finishing operations. The concentration visible on workers' faces during this delicate trimming phase reveals their awareness of what's at stake. A few millimeters of excess material removed incorrectly could potentially compromise the entire casting after so many hours of work. The manufacturing journey concludes with comprehensive quality control inspections for each industrial component. Once approved, parts receive specialized protective treatments like anti-corrosion coatings or industrial-grade paint systems, preparing them for years of reliable service in demanding environments. Through all these fascinating processes, we've discovered that Pakistan's manufacturing workforce represents something far greater than mere industrial capacity.